pure simulation and build a noise model. So the goal at the moment is to create this upper operator that you see here, right? It's based on the Pauli noise. And we have a lot of freedom to decide how to disturb the pure density matrix. So as Matteo explained before, you have these two elements. The first one, which is just rescaling the density matrix, and the other part, which is adding noise following the Pauli noise approach. You have some probabilities to be set, and usually the first question is, why do you use these? What is the relationship between these and real experiment? Well, it's the fact that we are trying to deteriorate the pure matrix with some specific noise reconstruction, and usually this is very simple to do, and from the experimental point of view, results are pretty consistent. So it's possible to find a proper set of probabilities based on the Pauli gates that generate results similar or close enough to what you see in experiments. But obviously, the equation that you see here is not the best. If you, for example, if you consider more advanced models based even on machine learning, you can try to create something extremely robust that replicates and imitates the circuit behavior. But for the sake of this tutorial, we are planning just to do simple things. So we are trying to apply the Pauli noise, which is very simple also to understand. And the first thing we have to do in Kibo, there are many interfaces to noise. The one that I use here is the approach based on a dictionary, where I create a noise map. So this is my dictionary. And the noise map will associate to each qubit a specific list of noise, in particular gates, in this case. So for example, for qubit 0, you create a list where I put together the Pauli X and Pauli Z. And I would use the syntax, which is a little bit tricky, but there's nothing special from that. So I'm just zipping the X and the Z gates together with some probabilities. So the pk that you see in the equation here. So qubit 0 will have a probability of 0.007, so 0.7% for X, and a probability, for example, of 0.8%. Yes.
Can you see? More?
More? Ah, come on.
Just ask it.
You put next time you can put.
Huh?
Sorry?
Just a little more, please.
Yeah.
That's fine.
Thank you.
Can you see?
I also need to update my glasses, so
No. Next time in the requirements we put bring a telescope, and that's okay. Together with your laptop.
Or the ophthalmological visit.
It's a condition. Huh? Okay, 0.7% for X and 0.10% for Z. So it's very slow, very small, but still it's something that is not negligible. We repeated this process for the other qubits. Here I have the qubit 1. I will do the Y gate together with the Z gate. And for probabilities, we can use 1% for Y and 0.5% for Z. And the last qubit, so qubit 2, is another list with, in this case, let's do X and Z with probabilities 0.8 and 0.7%. Okay, good. So this is the noise map. Now the goal is to introduce, to ask Kibo to take in consideration this dictionary and apply the model on top of our circuit execution. Now the best we can do to do not to break the infrastructure and the layout of our circuit model is to just allocate a new variable that you call noisy C. So the noisy C version of the circuit, and this noisy C will be our circuit C dot with Pauli noise, and this function accepts the noise map. So the method with Pauli noise is some sort of circuit factory that creates a new system, a new circuit object with all the extra gates that are needed to control, to introduce the Pauli probabilities. In fact, if we print this new circuit, so if I do print noisy C.draw, now I have it to unzoom, otherwise you cannot see it. Yeah. This is the new version of our circuit. And if you compare it, so I can compare here, let me do it C.draw. Let's put a print. Okay, so the first one is the new circuit with the noise model, and the second one, so this second part here, is our original circuit without noise. Yep.
What is the PN gate?
Pauli noise.
Pauli noise.
We are applying the randomly x or a z to the first qubit and y or a z to the second qubit. So in the first line, each Pn is basically a sequential application of randomly an x gate and a z gate with that probabilities we defined before.
Yep.
After each gate, we apply to each qubit a Pauli noise channel.
Yeah. And by the way, if you put inside the draw method the legend equal true, this will create a table at the bottom of your circuit with some sort of mapping between the gate name and the symbol. So as you said, gate Pauli noise channel corresponds to the symbol Pn. Only for the gates that are not, things that we are defining Gibo, because Pn is not for sure standard nomenclature for noise. No? It's something that we defined internally because we wanted to keep it simple. In fact, many people, when looking at Gibo, or in particular when looking at this draw, and when comparing to Qiskit and other, they complain about, yeah, Qiskit is much more fancy, shows a lot of stuff. No? But we did that. We decided to use this layout exactly for simplicity. So we didn't want to make it a gigantic draw. We wanted to keep it simple, so you can really see. And then if there are maybe ambiguities, you can have a look at the legend, and that's it. Okay. So now, what next? If you take the noise C and we do get parameters, you see that we have some numbers that are already based on those from the original circuit. So we, in principle, don't have to set it again. So we are almost ready to run. Therefore, we go here and we start doing our noisy final state. So we follow exactly what we did before. This will be noisy C open and shots equal 2000. And then we compute the frequencies. So noise frequencies equal to noise final state dot frequencies with binary true. And now we can plot the histogram. So we do plot scripts dot visualize state, and we pass the noisy frequencies. Sorry, yeah, the frequencies and the noise frequency. So I'm asking the visualized stage to plot both distributions together, the original without noise and the version with noise. Okay, so let's try. And here you have. So as you can see, the magenta distribution is the noiseless simulation, and this is exactly the same plot that we showed above. While the transparent histogram with this special shader corresponds to the noisy version of our circuit. So the noise that we have introduced is not extremely large. That's why you get a distribution that is close enough to the original target. But now, if I increase the probabilities, I can see a strong difference. For example, if I go up and instead of putting 007, I do something crazy like 7 and 8 for the first qubit, 5 and 1 for the second one. So I reduce by 1 order of magnitude all the sources of noise. Everything will be exactly the same, except that now the simulation has changed a lot. No? I'm deteriorating a lot the quality of my circuit simulation. So as you can see, I'm also getting something flat. So our goal from a theoretical perspective is to find an algorithm that can, for example, get the distribution, the white distribution, and correct and mitigate the uncertainties by recovering the noiseless simulation. So this is the most challenging part of all the recent works in quantum computing, and is a crucial step, because if you get noisy results, you cannot do much. No? You are locked into that. Okay, is that clear? Good. So now let me try to plot again the density matrix. I just copy what I did here and paste, and change, instead of C, I do noisy C. And voila, you get a diagonal density matrix. Okay? So as expected, if the noise is extremely strong, as we have implemented here, our mixture, our density matrix will fall back into a diagonal state. We have a diagonal shape. Okay. Well, last step is to check out the observable prediction, also in this case, and compare. So our noisy observable, or noisy expectation, will be the observable expectation from samples. And let me zoom back.
The last line. Good come here.
Okay, noise frequencies, and now we print the value. So we have let's print the two values. So first one will be the noiseless expectation value.
Can I ask a question before?
Yes.
Question. What you expect now?
Yes.
So the noisy expectation value. What do you expect from it with respect to the noiseless expectation value? It was 0.6, if I remember correctly. What do you expect in this scenario? Yes. You remember the comment in the red box in the lecture? The effect of this Pauli noise channel on the system is to push the expectation value of Pauli strings like this, because it's a Z, to which value? 0. So in principle, we expect, depending on the magnitude of the noise, this is getting stretched, not stretched, pushed to 0.
Okay. So if that's the case, let's see it numerically. And here we go. The theoretical expectation without noise is 0.63. And now we get 0.27. Okay. Strong reduction. Okay, questions? So in this tutorial you have seen a very simple, very basic example of how to introduce noise based on the Pauli approach to a circuit. Now the question is, how can I mitigate these errors? How can I recover the original value? And now Matteo will show us the mitigation of noise using the Clifford data regression. Yes.
Can I get a negative expression value?
Depend on the observable. But this, yeah, this is a this Z, which is a global Z, like you are applying a sequence of Zs. If you look to the eigenvalues, you have among -3 and +3. Indeed, the expectation value of the observable over the final state will be something between these two values here. You can also use the probability directly, and in that case is positive, definite positive. Okay, so in the second part of the lecture, we see how to mitigate the noise using Clifford data regression that we saw. Thanks to the Kibo headphones, our mongoose is now no more suffering for the noise. Yeah, it's just for the joke. Okay, so as usual, there is some fast explanation about quantum error correction and quantum error mitigation, but we already saw it in the theoretical part. So we can go, and as usual, if you need to install again KiboJit and KiboJit, actually no, Kiboido. And then we proceed with the imports, okay? So let me import NumPy and Matplotlib again. From Matplotlib. Oh, sorry. Okay. Then we need Kibo. Then again, we import usually circuit gates and Hamiltonians. And now, since we are going to define the noise model in a different way, so that the one we saw before was a shortcut with Pauli noise. You apply directly to the circuit object, and that's indeed a shortcut only if you want to deploy some Pauli noise channel. In general, in Kibo, you saw from the theoretical lecture, we have many channels, and you can build your custom channel by combining different gates and different channels, indeed. So in this case, let me import some useful methods, modules, which are, okay, from Kibo.models, import error mitigation. Let me import error mitigation, which is a collection of techniques of error mitigation. Among them, you can find the Clifford data regression. And then we import from Kibo.noise, import Pauli error and noise model, which is the abstract object on top of which we build our noise model indeed. Okay. like before, we can check the backend. Kibojit in our case. And then we should start again the discussion about the Clifford data regression.
Come back a little bit.
Oh, yes. Okay. So we need to define basically the same problem of before. If you want, you can do copy-paste. I will code it again, but will be the same definition of before. So n qubits equal to 3, because we want to take the same example, the same noise model, and then try to apply the error mitigation technique. And layers equal to 3 again. Then we define the circuit, n qubits, and density matrix equal to true. Okay? Yes?
What is the backend?
Opa. Here. Get backend. This is just to check it, but if you don't type anything, you just by default activate the backend you have installed. If you installed Kibojit, you activate Kibojit. If you don't have Kibojit, NumPy. Okay? And then we go on and we build the same structure of before. So we need to loop over the layers. Then we loop over the qubits. Then we apply the rotations, Ry, Rz, if you remember. Yep. The Rz now. Okay. Now we add some entanglement, so some CNOT gates for Q and range. Remember, we should loop from 0 to n qubits minus 1 with step 1. And then we add gates.cnot with Q0 equal to Q and Q1 equal to Q plus 1. Finally, we can add the measurements. Okay? Do you need me to zoom? Fine. Okay. So now we have our circuit, which is the same of before. Let me set the same set of angles. If you remember, we need a number of parameters, which is equal to the length of the output of the c.get parameters function. So the number, we are getting the number of parameters of the circuit. And then we can define the angles as np.linspace from 0 to 2 pi of n params. We want a number of points equal to n params, which are equally distributed from 0 to pi, like before, the same set of angles. Okay. Then we set these angles into the circuit. So c.set angles, so parameters, sorry. We We call them angles because in this case the parameters are actually angles because we use rotations, okay? We can print the circuit. And finally, we can define the observable. So we have all the ingredients, we define it in the other notebook. So our observable will be Hamiltonians dot z and qubits equal to n qubits, and that's all. If you remember, we printed the circuit, so we have the output, which is the same circuit of before. We can also print the parameters if you like, just to double check. Using the circuit.getParameters function. Okay. Okay, so now we set the same problem of before. The next step is the one of generating. This will be done inside the function we have in Kibo, but in general, in the Clifford data regression, we need to generate a set of circuits which are of the same size of the target circuit, you remember, but with some of the gates are replaced with Clifford gates. In the case of the rotations, is important, this step. A rotation with a general angle, a random angle, is not a Clifford gate in general. But if you replace the angle with a multiple of pi half, then the gate will become a Clifford gate, okay? This is the game in this case. We have a circuit which is mostly composed of non-Clifford gates because they are rotations with random angles, and the C-nots which are Clifford gates. So we are not going to touch the C-nots. For now, we just look to the rotations. And what we are going to do is to replace some of the angles of the rotations with not random, but multiple of pi half. Okay? So let's check what happens if we generate a random circuit using the Clifford data regression requirements. Let me call it CDR circuit. And now from the Kibo error mitigation module, we can call the error mitigation dot sample training circuit CDR function. And what you just need to do here is to provide this function with the circuit you want to sample from. Okay? So you just set C, which is your target circuit, and the method will be automatically check the circuit gates, detect the list of non-Clifford gates, and replace some of the parameters of these gates with angles which make them Clifford. It's clear? Okay. So, okay, this is again a circuit. We can, for example, print it. So print c.draw. You will see the shape is the same of before. Sorry, this is the one of before, so for sure it's the same of before. But if we print CDR circuit, also, we can print them all together, maybe it's better. So print c.draw, and then we can make some space here. And then we print also the other one. But okay, you see, the CDR circuit has the same shape of the C. And this is what we want, because we don't want to change the noise model. If we assume the noise model is related to the number of gates, the depth of the circuit, and so on, then it's important to preserve the same size, the same architecture in the end. Okay. And with rotation, it's very nice, because you can replace you just replace the angles, and you get a Clifford data regression circuit. Okay? So if we want to check the angles, just to be sure, again, let me do some space here. Oops. We can print the angles before and after, so print c.get parameters, again, we do like this. And then we print CDR circuit dot get parameters. Let's check. Okay, already from the first angle, you will see this one is pi half, 1.57. I mean, you can check if you want by dividing pi by 2. But some of the angles are replaced, some not. Like the second, there is 0, the second angle is replaced, the third one no. So randomly, we are replacing some angle in the circuit. So some of the gates have become Clifford, and the others are still non-Clifford gates. Okay? Okay, this is automatically implemented in a method which we are going to call, which is Clifford data regression indeed, okay? But let me, this we already did, compare circuit shape and angles, okay? So now we need to complicate the problem, because for now these circuits are noiseless. They are still a circuit in not exact simulation, but yeah, exact in the sense of without noise. We can use shot noise, but not proper noise. So we need to create a noise channel and apply again the noise channel to the circuit. Before we used the circuit dot with Pauli noise method. Now we build a proper noise channel in Kibo. To do this, we can create a noise object, which is initialized calling the noise model class. And then we need to add sequentially to this noise model the same Pauli noise channels we were defining the last lecture, the last notebook. So noise.add, this is a slightly different notation, but we are going to do the same of before. Okay? And we add Pauli error. And Pauli error needs something very similar to the noise map you saw before, but just one element of the noise map. Okay? So we add a first contamination, which is an X gate, if you remember. And the probability was 0.007. The second contamination is a Z with probability 0.008. And then we need to specify to the Pauli error, sorry, to the noise model. So in the moment in which you add this error, you need to specify to which qubit you want to apply the contamination. Okay? So in which case we say qubits equal to 0, because we want to apply this Pauli noise channel only to the qubit 0, like we were doing before. Okay. Now, let me, okay, now we can do it from scratch. We need to add also the noise channel to the qubit number 1 and the qubit number 2. So noise.add Pauli error. Again, we open the, oops, sorry. We need the parentheses. Okay. Now. Yes. Now it's correct. Should be correct.
No, in the line above.
Sure? No. Should be correct. Let's check. Yes, that's correct. Okay. If you remember, we were adding the Y and the Z to the second qubit. So Y, and then the probability was 0.01. And the second was a Z with probability 0.005. Yes, correct. And then we define the qubit on which we want to act, and again, qubits equal to 1. Okay, this is working. Finally, we need to add the contamination to the third qubit, so noise.add Pauli error. And then we need to add an X and a Z again. So it was an X gate with probability 0.008. And a second Z with probability 0.007 to the qubit number 2. Okay, so now we have our noise model. Let me check the question in the chat. Ah, yes, sure. I was coding from scratch, but we can also do copy-paste, of course. It was on purpose. Okay, now we need to apply the Clifford data regression technique. Luckily, we have already the method implemented in Kibo. You just need to call it. And let me show you how to do it in the full picture, if you want. So you can, from the error mitigation module, we can call the CDR technique. The output of this method depends on an argument of the function. I will show you now, but for now, we can collect some output from the function, which are mit_exp, which is the mitigated value of the expectation value, okay? The noisy exp, the fit parameters, that depends on the fit, the model you assume to fit that cluster of points I showed you before. By default is a line, as I was showing in the slide, but you can define any callable function, parametric, of course, and then you will get in return the parameters after the fit. You will see what we get in these fit parameters will be just two values, the slope and the intercept of the line. And then the training data. And the training data will be the expectation values, exact and noisy, for all the Clifford data regression circuits we generated on top of the target. If we set 100 circuits, you will get two lists with the noisy expectation values and the exact expectation values. This will be returned by a function which is error mitigation .cdr, like Clifford data regression. And now we need to provide it with some arguments. The first argument is the circuit, the target circuit, because inside the function will be generated a Clifford data regression circuit on top of this circuit, which is C. Then we need to know the observable we want to mitigate. So observable, which is equal to obs, which is defined above. Let me check. Should be here. Yes, obs. Okay. Then we need a noise model, because we want to contaminate the circuit with the noise model. In this case, the noise model is noise, because we created it here. Then you need to define a number of shots to compute the Clifford data regression, because we are going to to execute many times the circuit and to collect noisy and exact expectation values. And for the noisy one, we need the number of shots. For example, we can set 50,000. Then we need to define how many circuits we want to create. The Clifford circuit, Clifford data regression circuits. And the argument is n training samples, number of training samples. For example, we can set it to be 50. Of course, the higher this number, the more precise is the representation of the noise, because you have more circuits. Another comment important to say is that if you have a circuit composed of 4 gates, you cannot sample an infinite amount of different Clifford data regression circuits, but you have a few possibilities because you have just 4 gates to be replaced, no? If you have a huge circuit, you can create a huge sample. So these should be a trade-off somewhere, okay? And then just let me activate the full output argument, which enable us to collect all the mitigated expectation value, the noisy, the fit parameters, and the training data. If you set full output equal to false, you just get the mitigated expectation value. We set true, and everything is set up. So now this can take some time, but we need to execute it. The Clifford data regression technique is running and is generating the circuits. Okay, we finished. Computing exact expectation values, noisy expectation values, fitting the cluster, and then mapping the initial circuit through the map, which is the line. Again, here we were listing what you get as output of the function, but you already know now. And now we can just check what is going on. So let me plot the results. Okay. So now again some fancy plot. So let me at first define a line, so a next line, just because I want to plot the fit. Okay. np.linspace between, let's say, probably we will stay around 0.2 minus 0.2, and we should tune this after the result. We will see. Let me stay in this range for now, and 100 points. So this is just to plot the line, okay? I'm just taking some points on the x-axis. Then the y, so the line, will be dependent on the fit parameters we got thanks to the Clifford data regression technique. In particular, we have the slope and the intercept. So let me do fit params of 0, which is the slope. So we multiply it with x, plus the fit params of 1. So in principle, now we should have a line. And now we build a figure in matplotlib, and we plot everything. So pld.figure. So this, again, is not super important. You can just decide the size you prefer. Okay, then let me set a title. An X label and Y label. Then we need to plot the line, so plt.plot x, y. Let me set some color, like black, some line style, like dashed line, and a label. We can call it fit or CDR fit if you want. Or we can already start plotting this if you want. So we see the plot growing. So for now we have a line, just a line. Then we should plot the noisy and the exact expectation values to see if this line is actually fitting the points. So plt.scatter. And the output was training data, if you remember. And training data is a dictionary containing two lists. The first one is called noisy, which collects all the noisy expectation values. And the second one, same training data. And the key is noise-free. Let me set a color. Usual palette of the notebooks. Some opacity. This is not very important again, but some size for the markers. The dimension of the points in the scatter plot, and then a label, which is training circuits. So again, I can show you from the beginning. Training data of noisy, then training data of noise-free, and yes?
Can you just go on alpha and just click enter?
I press enter, you mean?
In the scatter line,
Uh-huh.
just click enter.
Ah, yes, thanks. Thanks, you're right. Good advice. Okay? And then let me plot also what in principle should be the axis. Okay, so the x and the y axis. So we need a vertical line in 0. And again, we go from minus 0.2 to 0.8. This is because we should stay between minus 1 and plus 1. Then we should understand where we are. Probably we are in this range again, because it was 0.6, the expected value at the beginning. Let me do this to be sure. Then color black. And the line style continuous line. And we want a very tiny line. So line width equal to 1. And then an horizontal line, which is the x-axis, so plt dot x lines. 0, minus 0.2, 0.8, color black. Same line style, same line width. Error. See, it's horizontal lines, so it's AH lines. Okay, this is what we get. Let me dezoom a bit. Okay, so in the end, our expectation values of the 50 points of the training set were distributed along this line, which is between minus 1 and plus 1, which are the extremes of our expectation value possibilities. And varying the gates inside the circuits, we are varying the circuit enough to see some changes over this line. And this is enough to get fitted. And in the end, what happens is that we can exploit this slope and the intercept with the y-axis to characterize, in some sense, the noise we have in the problem. Okay? So this is actually what we studied in the Clifford data regression. Then what we can do is to see if, in the end, mitigate the expectation value, which is just the map of the expectation values we get the noisy one through this line here. So we take the point on the x-axis and we map it on the y, is better than the noisy case or not. So closer to the theoretical value. So let me print it. So print F. Let me zoom. Okay. Noisy xBOV, expectation value, is noisy exp we got from the Clifford data regression. And then we have the mitigated expectation values. And if you remember, just let me print also the exact value. Was something close to, it was depending on the number of shots, but it was something close to 0.6, like 0.602. Okay. If you want to have the exact value, you just need to compute expectation instead of expectation from samples, and you will have the exact value from the exact simulation. So, as we can see from the numbers, of course, we didn't reconstruct exactly the value we wanted, because we still have some effect of the noise. We are mitigating the noise. We are not removing totally the noise. But the value we get is much more reliable than the previous one. So we jumped from a 0.33 to a 0.57, which is closer to 0.6. Okay? And this is important to understand because error mitigation can be very useful with the NISC devices. Someone of you mentioned the NISC devices, no? Noise intermediate scale quantum devices, with a few number of qubits and noisy. But you don't need huge number of ancillas or strange setup that's unfeasible today, you already can execute this in a current laboratory nowadays to get more consistent results with respect to the pure noisy results. Okay? Yeah, that's all for this lecture, I would say. I don't know if you have any question.
Matteo, it's a really clever technique, but does it work in real life?
Yes, it works.
Like this or?
No, like this. I can show you something if you want. Can I go into?
Okay.
So I would refer to this kind of work because it's mine. So I can motivate what is written here. This is a paper from our group. I did together with Stefano and other people. Here basically we were using a more complex technique, which is not the Clifford data regression, but the important Clifford sampling, but it's similar in terms of concept. Okay. These were the target circuits, so just rotations, whatever you want. And we can go to the simulations maybe. And here we were applying a gradient descent, and each expectation value in the gradient descent, so both when you were computing the predictions, which were expectation values, and the gradients, which were expectation values, we used this technique to mitigate the results. This was a function you already saw yesterday. It's the up quark partial distribution function. Let me zoom again. The blue line is the training performed in a noisy environment simulation. The red and the green are the training in noiseless environment, and the red is the training with the real-time error mitigation with this technique, which are basically the same line. So in the end, we were mitigating the result. This is simulation. You can complain about this is just simulation, and with 1 qubit because that model was with 1 qubit. These models are multi-dimensional with number of qubits 4, 6, and 8. Slightly different model of noise, but basically the same. We also added some readout noise channel. It's a more complicated noise, but in general, the technique is working also here. In the last one, you see the noise model is not enough reliable to be able to do the things properly. You start to see some difference between the black line, which is the target, and our estimations. But again, between the blue line and the red and the green, there is a huge gap. And this one, finally, let's go here, is the case, okay, maybe this is easier before. This is on actual superconducting qubit. Go up, okay. The blue line, okay, this fit is not amazing, but the blue line is the one with noise without mitigation, and you can see it's below the black line, which is a sort of quantification of the noise, which is the qubit fidelity, but in the end, some way to compute the noise of the lab. And if we go to better trainings, so longer trainings, you see the plots are much better. And these were obtained by doing real-time quantum error mitigation on a real superconducting qubit. Of course, it's 1 qubit. It's not super huge example, but just to prove that in practice can work. Probably if you scale up with qubits and you have a different model of noise, at some point you will see that this technique is no more able to perform the mitigation perfectly.
But is this a method that may work with any noisy model, or there is a specific noisy model which it works?
It can be quite general, but if you start to take into account the coherence, like the depolarizing, not depolarizing, let me check the names, different noise models, like the thermal relaxation, these kind of models, then is no more 100% reliable. The Clifford data regression, as it is. I cannot explain you, I think, more in details why. We can discuss if you want. But I know that's not 100% reliable in some situations. I think in the original paper of the Clifford data regression this is mentioned. Actually, I don't know the answer now. Empirically, I would say that you need to look at the final plot and to see if you are mapping well between -1 and +1. But to a better answer, I would check in the reference. It's in the slides. The name of the reference is Error Mitigation with Clifford Quantum Circuit Data. Is the last one in the slide number 8 of this block of slides. Question from Zoom? Then I come there. I have a question about the way to use Kibo. If I just import Kibo and instead of doing from Kibo import some method of from Kibo.some module import, okay? Can I use this method in the following way? Yes, you can. Yes, you can. Should can. Actually, I would pay attention to this a bit because some of the methods are imported. I mean, we have some shortcut in the imports. So, for example, the circuit is not from Kibo.circuit, but is Kibo.models.circuit.circuit. So if you follow the notation we explained, it is better. If not, you just open the code and you follow the standard import procedure, following the folder structure.
I am seeing that in the Kibo.edu repository are you updating the final notebooks with the calculated code and so on. This is going to happen also for the notebook number 3, number 5, and number 8 because those notebooks didn't use this
Number 3, number 5, you should already have it.
Where?
In the main.
I think number 5 is something more about the Gruber.
Yes.
And the number 8 is currently is not touched.
Yeah. The number 8 is about the variational quantum eigensolver. I don't think we have time now to do that, but if you are interested, there is a notebook about it. But yes, DZ.
Because I am seeing that the lecture number 3, the notebook number 3 has been already updated, and this is about which just
Yeah, because the full course also includes the Doi-Jodza algorithm and the variational quantum eigensolver. But
I am asking, this is going to happen also for the.
yeah, we upload all the notebooks complete probably this evening or tomorrow.
Okay, thanks.
From 1 to 5, you should already have it, if you check.
5 is currently 8 is not.
No, 8 no, because 8 we were planning to do it today.
Thanks.
Okay, if you are okay in jumping the break, if you are okay, we can have a look to the variational quantum eigensolver. If you are okay. By raise of hands if you want. So I would ask if you want, who among you wants to do the VQE? Because, okay. Or, yeah, we can, okay. Not,
Could you repeat the question? I didn't hear you.
I was asking if you want to do the break, but then I don't know if we have enough time to do the variational quantum eigensolver, or if you want to skip the break and doing the variational quantum eigensolver. But typically, if I ask if you want to skip the break, no one raised the hand because they are bad people. No, but from chat they call VQE. Okay, so for doing this, we need to just, you can, I think, take like 3 or 5 minutes of break because we prepare it, but then we start.